Okay, so here we'll talk about the Lenz's law. So here we'll see why we need to mention a negative sign as Lenz's law, because this negative sign is not that easy to determine. Okay, actually, I mean the direction of the EMF is not that trivial. Okay, because it is related to the derivative. Okay, so we need to see how the B field or the magnetic flux is changing. Okay, so it says the induced current has a direction such that the magnetic field due to this induced current opposes the change in the magnetic flux that induced the current. Okay, so this is the Lenz's law. Okay, so yeah, so this is the description of the Lenz's law. So yeah, you don't feel like what it is, but yeah. Okay, so here it says the Lenz's law at work as the magnet is moved toward the loop. A current is induced in the loop, and then the current produces its own magnetic field with the magnet dipole moment oriented so as to oppose the motion of the magnet. Okay, so here it says like yeah, so here if you put the magnet bar, okay, initially far away, okay, so the magnetic field generated by this magnetic part across this cross section will be very small, so you approximate it to be 0. So if you put this magnet bar close to this loop, okay, so the B field line generated by this magnet bar will be something like this, and then if you push closer and closer, the magnetic flux across this cross section will be larger and larger. Okay, so in this case, this loop will try to generate the B field so that to opposite the change of the magnetic flux here. Okay, so in that case, because the magnetic flux is going in this direction and then becomes larger, so it tries to generate a current in certain direction, and this current will generate the B field in this direction, so that it try to cancel a bit, not necessarily cancel a bit of this change. Okay, so in this case, it need to generate the B field pointing upward, so the direction of the current will be like this, like counterclockwise. If you slightly look from the top. Okay, so here is the demonstration of the Faraday of the Lenz's law. So here it says starting from the top left. Okay, so it says so the induced current rate create this field trying to offset the change. So it says increasing the external field B induce a current with a field B induced that opposite the change. So this is the initial setup. Okay, so here is the loop. And then here we have the B induced. Okay, so just ignore it first. We have the B field pointing downward. So this all the way, this B means the external B field for all these 12 figures. So this is generated by externally. External. This is external. Okay, so if this B field is increasing, okay, so it says B field is increasing the external increasing the external B field. Okay, so this B field is this one and then become larger So in this case, the magnetic flux across this loop, will be increasing and then pointing downward. So in this case, this loop will try to generate an induced B field pointing upward. We try to cancel this kind of change, even though this B field cannot, this B induced cannot perfectly cancel the change, but it try to do so. So the B induced will be pointing upward. The B induced will be pointing upward. And in this case, using the right hand rule, your thumb pointing upward, and then your finger will be counterclockwise. Okay, so it means that if B is increasing, okay, this is the induced current, and then this is the induced B field generated by this induced current. Okay, so the next case is the B field, the external B field increase until this is the maximum point, and then it start to decrease. Okay, so in this case, the external B field is still pointing downward, but it start to decrease. Okay, so this one is starting to decrease. So the magnetic flux pointing downward becomes smaller. The B field, the magnetic flux becomes smaller. Okay, so which means that this is the direction of the magnetic flux, but it becomes smaller. Okay, so this loop will try to it feels that the magnetic flux here is becoming smaller, so he tried to generate B induced pointing downward, so that to compensate this change. We try to compensate this change, so the B induced will be pointing downward, and then using the right hand rule, your thumb pointing downward, and then your forefinger will be in this direction. So this is the induced current. So for this one, B field pointing downward increasing, and then the current will be counterclockwise. But for this one, B field also pointing downward, but B field is decreasing, then the current is clockwise. Okay, so this is counterclockwise, this is clockwise. So which means that the current itself doesn't related to, actually related to, but not determined by the external B field direction. Okay, it's also related to how the B field change. Okay, so the third case is that the B field start to decrease up to 0, and then it further decrease, so it start to pointing upward. And it is actually increasing. Okay, so this is increasing. So this B field is pointing upward and increasing. Okay, so here the phi B is like pointing upward, and so this loop will try to generate B induced pointing downward to cancel this change. Okay, so here B induced pointing downward, so I is clockwise. Okay, so the direction here and here is the same. Okay, so here external B field pointing downward decreasing, here the B field pointing upward and then start to decrease. Okay, we'll have the same direction of the induced current. Okay, so the final case is that this B field, this external B field started to increase until the maximum point, and then it start to decrease. So this B field start to decrease. So this loop will try to cancel this change. Okay, try to cancel this change. Okay, so in this case, the B induced is pointing upward. Okay, using the right hand rule, your thumb pointing upward, your forefinger will be like counterclockwise. So in simply speaking, these two have the same induced current direction. These two have the same induced current direction. Of course, it is related to this one. E equals negative d phi b dt. Okay. Yeah, if you just look at this is the phi b direction, and then you see how it changed. If it is increasing, okay, and then due to this negative side, okay, it will point to the opposite side, which means that this is how the phi b is changing. And then this minus sign means it try to compensate it. It points to the opposite direction of this phi b change. So that's why we call this one, this negative side, to be the Lenz's law. Okay, so here is a sample problem. So it says a conducting loop consisting of a half circle of radius r. Okay, so this is small r, and 3 strict section. Okay, this 1, 2, 3 strict section. Okay, the half circle lies in a uniform magnetic field B that is direct out of the page. Okay, so you can see the green dot, meaning the B field. The B field are pointing out of the page. Okay, the half circle lies in the field magnitude is given by B equals to 4t squared plus 2t plus 3. Okay, so this B field is time varying. Okay, so it will change in different time. Okay, so with B in Tesla and T in second. Okay, an ideal battery with EMF EBAT. Okay, so this is EBAT equals 2 volt is connected to the loop. The resistance of the loop is 2 ohm. Okay, so the 2 ohm is across the whole loop, so it does not draw it out explicitly, but the resistance of the loop is 2 ohm. Okay, what are the magnitude and direction of the EMF induced around the loop by the field at t equals 10 seconds. Okay, for different time the EMF is different. Yeah, you can expect the derivative of it. Okay, will still depend on time, and then you substitute different number of time, different time moment, and then this value will be different. Okay, so it asks you what is the EMF, the induced EMF at t equals 10 seconds. Okay, so here we can see E induced should be equals to negative d phi b dt. Here we only consider the magnitude. We only consider the magnitude. So we take the absolute value. Finally, we can determine the direction of the current, yeah, by the Lenz's law independently. Okay, so here absolute of it will be d phi b dt without the negative sign. Or maybe you can still take the absolute value because the derivative itself may not be positive. Okay, if you are careful enough, you can just take the absolute value here. Yeah, so here this is actually d phi b will be b times a dt. Okay, and actually the cross-section area doesn't change at all. The cross-section area doesn't change at all. So this a is a constant to the time t, so we can just put it outside. So we have a times dB dt, and then we can just plug in the value. Okay, so this is a half circle or semicircle, so we have a half of pi r squared. Half of pi r squared. R is here. R is 0.2 meter. Okay, so 0.2 square. And then we have d phi b dt. Okay, so we can write d dt, and then b is this expression, 4t squared plus 2t plus 3. Okay, so in the front it is still pi over 0.2 square over 2. Okay, so we just need to calculate it later. Okay, so we take the derivative, which is easy for the polynomial. Okay, so the derivative of 4t squared will be 8t. And then the derivative of 2t will be just 2. And then for the derivative of 3 is nothing but 0. Okay, so it is easy to take the derivative for a polynomial. Okay, and we would like to evaluate this one at t equals 10 seconds. Okay, so we just need to plug in t equals 10. Okay, so we have a pi over 0.2 square over 2, and then 8 times 10 plus 2. So this is nothing but a 5.2 volt. 5.2 volt. Okay, so this is the magnitude. This is the magnitude. It asks you what are the magnitude and also the direction. So we need to determine the direction. Okay, so here we can see B is actually 4t plus 2t plus 3. We can see that the derivative of it is still positive. The derivative of dB dt is like 8t plus 2. Okay, so this is still a positive number, which means that the B field is pointing out of the page, and also it is increasing. It's increasing. So according to the Lenz's law, the B induced should be pointing into the page. Maybe I should write it here. The B induced should be pointing into the page, right? According to the Lenz's law. Okay, so here we use a finger pointing into the page. Your forefinger will be like clockwise. I induced or I induced. Okay. So actually, this is also the direction of the EMF induced, EIND. Okay, so this is actually clockwise. Okay, so this is for question A, and then for question B. What is the current in the loop at t equals 10 seconds? What is the current? Okay. So just now we have EMF in this direction, and then the value is 5.2 volt. And then we also know that this E battery is 2 volt. Okay, so you just regard it independently. Okay, if we don't have the EMF, we just ignore all the B field change. If we only have this loop, and then this is the positive side, this is the negative side. So in this case, if you just ignore the B field change, the current should be in this direction. And then we can see that the EMF is in this direction. Also, this is the I induced or E induced EMF in the other way round. Okay, in the opposite direction. So finally, part of them will be cancelled. This 5.2 volt and this 2 volt will be partly cancelled. Okay, which means that we will have finally the current I to be 5.2 volt minus 2. This is the E battery. This is the E induced. And then over. So after subtracting, this is just like the potential difference. Okay, so we are using the Ohm's law. So the potential difference over the resistance. The resistance for the whole loop is 2 ohm. 2 ohm, okay, equals to I. So it's nothing but the Ohm's law. Okay, so this is 5.2 minus 2 is 3.2, over 2 is 1.68. 1.68. So we need to be careful about the direction. It is easy to make mistake. Okay, so next we have another sample problem. Okay, here we need some integration for this problem. So we can see it says the figure shows a rectangular loop of a wire immersed in a non-uniform and varying magnetic field B that is perpendicular to and direct into the page. Okay, so here we have the B field pointing into the page, and then this is the rectangular loop we are mentioning. Okay, the field magnitude is given by this one, B equals 4t squared x squared. So it is related to the time and also related to the x-axis. This is the x-axis. This is the x-axis. This is y-axis. Although the B field does not relate to the y-axis. Okay, so this is good news. Otherwise, we need to, if we need to calculate the B dot dA will not be, will be also equal to, will also related to the y-axis. Then that will be more complicated. It will be more complicated. But hopefully, it only related to time and x-axis coordinate only. Okay, so the loop has a width W equals 3 meters. Okay, W, this is 3 meters, and then the height is 2 meter. This is 2 meter. Okay, what are the magnitude and direction of the induced EMF around the loop at t equals 0.1 second? Okay. So yeah, so as much as we need to calculate the induced EMF, for sure we need to use the Faraday's law. Okay, if we need to use the Faraday's law, of course we need to calculate the magnetic flux. Okay, so phi b will be integration of b dot dA. Okay, for sure. And then b is perpendicular to this plane. Okay, so which means that b dot dA is nothing but b times dA. Okay, so here we try to do some variable change. Okay, so this dA, as much as the B field does not relate to the y-axis coordinate. Okay, so here we can just simply cut this whole rectangle into a tall one. So we just need to cut it like this. So within this one, okay, this is dx. This is dx as maybe I just highlight it here. So this is dx. The width is dx. So if this dx is small enough inside this whole rectangle, the B field should be a constant at a specific moment. For different rectangle, of course the B field might be different, but as much as we only need to cut it like this, then the B field is already a constant. If the B field is also related to the y-axis coordinate, for example, if B is like t square 4t square x square y, something like that, then we also need to cut it like this, and then we need to do dA change it to dx dy, but here we don't need to do so. To make it simple. So for this dA, let's see what is the area of it. The height is h, the width is dx, so which means that the dA should be h times dx, right? The area of a rectangle. So this is nothing but b times h dx. And of course, this x is from 0 to 3 meter. Okay, from 0 to 3 meter. Okay, so we can substitute the expression of b here. So we have an integration of 4t square x square and then dx from 0 to 3. Okay, so the only variable related to x is this x square. Okay, so we can just put 4t square outside and then integrating x square dx from 0 to 3. Okay, so the integration of a square will be x cubed over 3. So we have a 4t square and then x cubed over 3 evaluate from 0 to 3. Okay, which means it is 3 to the 3 cube over 3. 3 cube is 27 over 3 is 9. So 9 times 4 is 36 t square. Okay, so this is did I do something wrong? I forgot this h. I forgot this. Here we also have an h here. So let me see. I forgot this. Here we also have an h. Okay, let me just put it in red color. I forgot this h here. This is an h. So we also have a 2 here. So totally we should have 72 t square. Okay. Okay, so we can put in the number. Okay, so finally, E, the absolute value of E will be d phi b dt. d phi b dt. Okay, so this is phi b. Okay, so d phi b dt will be d 72t squared over dt. Okay, so it will be nothing but 144t. And then we evaluate this at t equals 0.1 second. So t equals 0.1 second will be 144 times 0.1, which is 14.4 volt. Okay, like this. Okay, so this is the magnitude and also the direction. For the direction, we can see B is pointing into the page. It is always positive. And then if T is larger, this one should be larger. You can clearly see that. Okay, so which means that B is pointing into the page and increasing, which means the B induced should be pointing out of the page. B induced should be pointing out of the page. Okay, so B induced pointing out of the page, you will use a thumb pointing out of the page. Our four fingers are like counterclockwise. Okay, so this is EIND or IIND. Okay, the induced current in this direction, which is actually like counterclockwise. Counterclockwise. Okay, so so here we talk about induction and energy transfer. Okay, energy transfer. So here it says a rectangular loop of wire width L. Okay, so here we can see this is the width. This is the width. This is the width. Has one end in a uniform external magnetic field that is direct perpendicular into the plane of the loop. So you can see this green cross means the B field is pointing into the page. Okay, and then we are grabbing a loop and then we try to pull it to the right side. Okay, we are trying to pulling this loop to the right side. Okay, so this field may be produced by a larger larger electromagnetic. Okay, so we don't consider how to generate it. We assume something generate this, and then the dashed line means the limit of the magnetic field, which means that inside this area we have magnetic field, and then outside the B field is 0. Okay, the fringing of the field at this edge is neglected. Okay, you are to pull this loop to the right at a constant velocity. Okay, so this is the setup, and then we try to pull this loop to the right side. Okay, and then it will generate some current, and then yeah. So yeah, actually it will generate a current. So let's see how to determine the direction of a current. So you can see. At first, maybe the whole loop is inside. Okay, so which means that the phi b will be maximized. So at first, phi b is larger. Phi b is larger and then becomes smaller because we are pulling this loop out of this region. Okay, the phi b will become smaller and smaller as much as integration of sorry, no circle here, b dot dA. So b is constant, so it's like b times a. So b doesn't change at this condition, and then a becomes smaller. Okay, so phi b becomes smaller. Okay, so here B is pointing into the page and becomes smaller. So which means that B induced for this loop should be also pointing into the page. Now you use your thumb pointing into the page, your forefinger will be like clockwise. So you can see this induced current is clockwise. Okay, so it says decreasing the area, decrease the flux, induce a current, and then this current is clockwise. And then it also tells you that there will be, now you know the current is clockwise. Then according to the Lorentz force in chapter 28, you know there will be force acting on this wire, because this wire are moving in the magnetic field. Okay, so here you can see for this one, this is outside, so there will be no force acting on it. And then for this one, the current is going from left to right, and then the B field is pointing into the page. Okay, so hope you still remember F is I times L cross B. Okay, L follow the direction of the I. So here you can see L is in this direction. So L cross B, L is pointing to the right side, and then B is pointing into the page. Okay, so F2, you can see F2 is pointing upward. And then for this one, you can see I is going like this. So here for this line, L is pointing to the left side. Okay, so L is pointing to the left side, L cross B into the page. So your thumb will be pointing downward. So you can see F3 is pointing downward. So you can see for this line, F2 pointing upward, F3 pointing downward. So these two forces will cancel each other. And then the remaining one, this one. Okay, so this one, L is pointing upward. So you use your finger pointing upward and then cross to B into the page. So your F1 is pointing to the left side. Which means that if you try to pull this loop out, pull this loop to the right side, there will be a force grabbing it back. Okay, so try to let you not be able to grab it out from the B field. Okay. So yeah, changing blah 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 to pull so there will be a work to do. Okay, so to pull the loop at a constant velocity v, you must apply a constant force to the loop, because a magnetic force of equal magnitude but opposite direction acts on the loop to oppose you. Okay, so here we also mentioned that the movement is in a constant velocity, which means that if it is constant velocity, so your force and this force should be equal, so that there will be no net force. If there is net force, there will be F equals ma. It's for the Newton's second law of motion. But here, as much as this movement is a constant velocity movement, okay, so the net force should be 0, which means that the force you apply should be equal to F1. Okay, so we just simply denote it as F, and then the work done will be F times V. This is not the work done, this is the power. And the work done is integration of F dot ds. Okay, even for the mechanics. Okay, F dot ds, and then integration will be the work done. And then for the power will be dw dt. Okay, so this is the energy. This is power. Okay, power is like the energy consumption in unit time. Okay, so it is like a d dt, and then integration of f dot ds, and then we assume that this derivative and this integration can exchange the order, and then we put it in, And as much as F is a constant, so yeah, so it's just a constant, then we can just put it like integration of F dot ds dt. Okay, so take the derivative of the displacement with respect to time will become the velocity. So it becomes integration of F dot v. So yeah, if all the things are constant, it will be like power will be F times v. So this is the work done, and then it actually tells you that actually this is the this is the work you do, and then all this work will be turning to the heat, okay, consumed by the resistance of the loop, okay. Yeah, actually, it's still telling you, okay. So here, it says, this is the magnetic flux. This is the magnetic flux. We still try to apply the Faraday's law, okay. So we first try to calculate the phi b. Phi b will be b times a. B times a. A is the cross section area. Okay, so and then b times a will be like L times x. X is here. Sorry, x is here. Yeah, from the left side to the boundary of the B field. Okay, so this is x. So x times L will be the cross section area. With the cross section area with the B field. Okay, so phi b will be b times L times x. And then we take the derivative of phi b will be the magnitude of the EMF. So we just put BLX here. BLX here. So we have d dt BLX. B is a constant. L is also a constant. So we can put BL outside. So we only have dx dt. Dx dt will be the velocity. So the EMF will be B times L times V. Okay, so this is the EMF. This is the EMF over the resistance of the loop. Over the resistance of the loop will be the current. So we can actually calculate all the things. Yeah. To find the magnitude, yeah, so nothing special. So we just go to the next page. Okay, so here we can also calculate the F1 due to the Coulomb, the Lorentz force, not Coulomb, the Lorentz force. Okay, so F1 will be like ILB and then sine of 90 degrees, nothing but 1. Okay, so F1 equals F equals I times L times B. I times L times B. And then this is I. This is I calculate on this page. I equals BLV over R. So here, I is BLV over R, and then times L times B. Okay, so here we have B square, L square, and then times V over R. So F equals B square, L square, V over R. And then finally, P equals FV. So finally, we multiply this one by V. So we have B square, L square, V square over R. So like this. Okay, so this is actually the work done for this movement. The work, the power due to this movement. Okay, so yeah, so note the work that you do is in pulling the loop through the magnetic field appears as thermal energy in the loop. Okay, so it becomes a heat. which is consumed by the resistor of the loop. Of course, this is a resistance across the whole loop, okay, but it only try to write it as a or draw it as a symbol, but actually it means the resistance over the whole loop. It does not add a resistance there. But as much as if you really try to do this experiment, try to pull it out, and then you will feel like the wire become hotter. Yeah, there will be thermal energy. Okay. Wow. Okay, so let me finish this page. Yeah. So here we talk about the induction and energy transfer, and then this is called eddy currents. Eddy currents in Chinese is called eddy, means 涡状. Okay. 就是漩涡的意思吧. Okay. So just now we have an explicit wire there. Okay, so you can easy to imagine, or if we try to pull this thing out, there will be a current going through this loop. Here, the difference is that here we have a broad of conductor. Okay. Yeah, so as you try to pull a solid conductor plate out of a magnetic field, eddy current are induced in the plate. Okay, there will be eddy current. A typical loop of eddy current is shown. Okay, there will be an eddy current. Of course, this is hard to explain how the current goes, because for the whole plane there will be some current. Okay, if you really need to know, you need to seek for some software to simulate this kind of structure, or how the current is going. Yeah, but at least I can tell you is that if you try to have this conductor board and then pulling it out from the magnetic field, and then which means that you are trying to changing the magnetic flux across this section. Okay, you make the magnetic flux become smaller and smaller, and then still according to the Faraday's law there will be induced EMF or induced current. Okay, this is only one of the loop, but actually for the whole board there should be some current there flowing like this. Okay, and this is called 涡状电流. Yeah, so maybe so next part will be, yes, this is actually still the Faraday's law, but originally this is E, this is E. Here we try to write it as an line integral. Okay, so next time we try to talk about that part. So